Very good. Let's continue where we left off yesterday. We made a list of the string field theories that are in reasonably good shape, and I talked about the open string field theory in lots of detail, and you will see material again in tomorrow's lecture by Martin and Friday's lecture by Yuji. Monday, yes, there's no Friday lecture. Monday lecture by Yuji. And so you will get to see more of the tools that are necessary to find classical solutions of open string field theory, which has been the reason why there's some progress in the field in the last few years, and several new ideas that still have to play out and may have implications for other string field theories, in fact. So I stick to my plan to explain a little about all these other string field theories rather than to go into more details of the open string field theory. I think there's a good chance that some of the ideas that are currently used need some clever modification to be applicable to other theories and may give us suggestions as to how to formulate better string field theories. So, in fact, there's probably a lot of interplay between the pure spinor ideas and the string field theory ideas that they can help each other make progress. So I'll just go ahead and continue explaining some of these string field theories. So the list we had started was open bosonic string, then closed strings, then open superstrings, and finally heterotic strings. So we have string field theories for all of those, and my goal is to give you a feeling, both algebraic and somewhat geometrical, as to why these string field theories work. In many ways, each of these string field theories required significant progress in order that they could be formulated. We've seen the open bosonic string field theory. People, or with them, had to realize that Q played an important role, and cube psi was an equation of motion, Q psi equals 0. It was also very clever to devise an associative multiplication. It's very difficult and very original. For closed strings, the main complication was, the small complication was what we dealt last time, the subsidiary conditions, B0 minus B0 bar. And the real complication was generating a cover of the moduli space of Riemann surfaces. And only when that problem was under control, we could write the closed string field theory. For the open superstring field theory, the problem has been picture changing, and in order to overcome that, we have the large Hilbert space and the ideas that Nathan used to formulate open superstring field theory. For heterotic string field theory, you do heterosis between an open bosonic string field theory and a Berkowitz superstring, and it's a rather original construction, how you can mix the two string field theories together. It remains to be done something for the type 2 superstrings, even in the Navier-Schwarz vector. And that has not been done yet, and it's, again, as you will see, it just seems if somebody would have a very clever idea, maybe it would actually be very natural and simple. So my goal in presenting these things is to just let you know what's happening, what have been the main ideas that succeeded, and maybe we'll get a feeling of where we have to go in order to make progress. So,
are you going to discuss what people type 2
I'm going to say a little bit of what fails. You will see the reason why there is a complication, at least, and you never know. You know, things look complicated and seem to fail, and you try something that and go ahead, but you will see why obvious things don't work. So we were doing the closed bosonic string, and one thing we decided was that the string field had to have a subsidiary condition B0 minus psi equals 0, L0 minus psi equals 0. The string field, in this case, modeled after the natural matter vertex operator acting on the vacuum or in some momentum. It's a ghost number 2 field, and it's Grassman even, as opposed to the open string field that natural being C times the matter vertex operator is Grassman odd. Now, we wrote a kinetic term. We said that the kinetic term, S2, would be 1/2 psi cube psi, but just with the definition that this inner product now, A, B, includes C0 minus, and C0 minus is C0 minus C0 bar over 2, C0 minus with B0 minus is equal to 1. So after you hide the C0 minus in the inner product, in the bilinear inner product, you write this term like this, and this action so far has a gauge invariance delta psi equal q lambda, where everything, lambda also satisfies this subsidiary condition, and lambda is ghost number 1, because this is ghost number 2, and Grassman odd. So this is the free theory, and now we have to do interactions. Now, how did we do open string interactions? We had the idea that the right half of the first string must coincide with the left half of the second string to form a third string, which was the product. This multiplication is associative, as we discussed, and it's certainly not commutative. If the right half of the first string coincides with the left half of the second string, you can multiply. But in this case, 2 times 1 doesn't work, because the right half of the second string doesn't coincide with the left half of the first. So it's definitely non-commutative, and that's very important. What happens in closed strings, however, is very different. In a closed string, people tried for years to define the best possible multiplication following Witten, but there was no solution that was dramatically successful. And the way you multiply closed strings here you have the first closed string, and the second closed string is here. And there's no notion of the beginning or end of the closed string, but in order to be possible to multiply them, half of the first string must coincide with half of the second string. That's the best multiplication you can devise. Once you have this, however, it's clear that if half of the first coincides with half of the second coincides with half of the first, and this product is naturally commutative. Up to signs at most if you have Grassman odd things, but this is a very different kind of object. This is not a star product. This is more like a Lie bracket, in which it's just either commutative or anti-commutative. xy is minus yx. So the product of closed strings should not be written as a star. The product of closed strings should be written as the product of two string fields is something like that. And it's graded commutative, so it's -1 to the AB BA. So that's a very significant difference between closed and open strings. Now, this, if you try to think even of associativity, in terms of associativity, you will see that there's a problem with associativity. Let me do one thing here. If you cannot speak of associativity, but suppose you had 1 times 2 and then you decided to multiply times 3. Well, suppose here is 3. Maybe this color is not clear enough. So it coincides like this and goes up here. Now, suppose this is 3 and you wanted to do 1 times 2 times 3. Well, you certainly can do 1 times 2. It gives you this closed string that is over here. And you can do times 3 now because half of 3 coincides with half of the product. But you could not do 2 times 3. So associativity is not the right language. You have a different situation now. So we have a product now. I want to say a couple more things about this product. This product has the property that the ghost number of AB is actually equal to the ghost number of A plus the ghost number of B minus 1. And the reason is the following. You have basically, we have the feeling that these products are essentially correlators using this geometry. But once you multiply, you must stay in the state space. And there's no reason why what you do naively of correlating two things will satisfy B0 minus. So B0 minus is imposed after you do this operation. Yes? No. Nobody has managed to do that. That's right. So if you could change that even at the kinetic term level, you would have a hope. You see, I have having played with this for a very long time, I know that if anybody will ever succeed to relax this will be a totally different beast. Will be fabulous, extraordinary. I don't think it's so easy. But
really both conditions necessary to happen following.
Well, these are a priori conditions without, you don't have to act with Q. These are a priori conditions on the state space. And for example, this condition is physically imposed just by pure cohomology. You know that if you study the cohomology problem in closed strings, you don't have physical states that violate this condition, for example. It's if a result of this workshop, this is relaxed, would be fabulous. Yes. Yes. Well, you see, ghost number 2, and that will be ghost number 3, and that is okay because look what we have here. Cube psi already is one ghost number more. So if you would say keep the logic, cube psi is not anymore a string field. So this is fine. This has ghost number 3, and this has ghost number 2 plus 1 ghost number is 6 that you must have here. So, but it's true. It doesn't map the product naively doesn't map that. But now we can add this interaction term, 1 over 3, psi, psi, psi. So this would be the cubic interaction term, and we could add here lambda psi. Yes?
So the program is the closest for that possibly directly, because we don't know where exactly to take the 2 points of the total thing.
Yes.
So it's not uniquely defined.
No, well, everything has, it's up to rotation, so it's completely well defined. Every closed string state has the L0 minus L0 bar constraint. So you average and sum over all these possibilities, basically. You're integrating over all possibilities of the points selected in doing the product. Why this product preserves what? Oh, I'm sorry, it doesn't preserve it either. So this product, operationally speaking, does the correlator, inserts a B0 minus, and projects to L0 minus L0 bar. Has to do all those things. You certainly want to project into L0 minus L0 bar, and you want to state, you see, this is the state space. We began with HCFT, but we reduced it down to some H closed that satisfies this, and we definitely want to stay within that space. So this product has those properties. Now, you can ask if this produces a gauge invariance, and it would produce a gauge invariance if this bracket that defines a Lie algebra, if you might think, satisfy the following condition: A, B, C, plus minus some signs, B, C, A, plus minus, depending on the statistics of these elements, C, A, B equals 0. If this would be true, if this bracket defined the Lie algebra by satisfying a Jacobi identity, then this would be gauge invariant. This would be the analog of what Witten did. You would have a cubic closed string field theory, and you would be done. The fact is, because of these issues that you have over here of rotation of a string, is that this, in a covariant theory, is never 0. And there are essentially theorems formulated by Sonoda and myself, not extraordinarily rigorous, but they're very convincing that there's no choice of any other picture of closed strings interacting that will manage to make this 0. Now, I want to emphasize, perhaps to illustrate, there's a little difference, for example, in the Lightcon that is very interesting. If you have in the Lightcon closed string field theory is cubic. So how does it manage, the Lightcon closed string field theory, to be cubic? Well, it is really a little bit like this. Suppose you have a string that we call A here, and a string that we call B here, and a string that we call C here. So the product of two closed strings in the Lightcon, like A times B, would be this whole string like this. Times C would be this whole string that would go like that. Now, if you look at this thing, you can certainly do B times C, that's this closed string, times A. This one exists. And also exists A times B times C. This one exists. This one doesn't exist. So actually this cancels that and you get 0. And that's how Jacobi works in the Lightcon. Nevertheless, covariantly, it just doesn't happen. And it can be done. So, how do you fix this problem? Questions or yes? Yes. It's just Lorentz symmetry. So actually, you need this Jacobi for J minus I. The Lightcon-Lorentz generator needs a Jacobi identity. So if you want to prove the Lorentz symmetry of the Lightcon, essentially you got down to the same or similar structures than in the covariant theory. So how do we fix this? This can be fixed in field theory if there exists a new product, a triple product, three strings, intrinsically new product in which three strings multiply to get another one. Well, because the Lightcon requires string lengths that must be attached to a physical quantity, P+, and you don't have that covariantly. Seems like a minor thing, but it's a tremendous problem. So basically, the closed strings in the Lightcon all are parameterized from 0 to 2 pi. Here, you admit a parameterization with P plus 1, P plus 2. This can have P plus 1 plus P plus 2, and it's twice as long. But you cannot, you sort of have to preserve length within the closed string, at least intuitively. So, how can you fix this? You can fix this if the failure of the Jacobi identity is equal to the failure of a new product to be a derivation of the BRST operator. So if Q on this, and what is the failure of this being a derivation? Minus QA, B, C, sines, A, QB, C, sines, A, B, QC. If this is true, if there is a three product whose failure to derivate is equal to the failure of the Jacobi identity, then you can go on, and this will be fixed by adding 1 over 4 factorial psi, the fourth product, and this will have a correction lambda psi, and you will save the gauge invariance. Well, you get the picture of what's going to happen here. You're going to need all of the products. Again, just like Einstein's theory is non-polynomial in the conventional variables, this theory is non-polynomial, and as far as we can tell, there's no simple trick to make it polynomial. If there's any way to make it polynomial, probably you will have to change something very deep about it. So, this kind of structure has a name in mathematics. It's called the Homotopy Lee Algebra. So it's a Lee algebra that doesn't have a Jacobi identity. There is up to a homotopy, it's called. The homotopy is provided by this thing. I want to give you there's more things with perhaps might be worth noticing the products. Yeah, I'm going to say something more about the products. These products, say B1, B2 up to Bn, such a ghost number property. So the ghost number, we saw the ghost number of this one, it reduced 1. So actually you certainly have minus 1, and then you have plus the ghost number of all the BI's. But there is a little more to this. When you have a 3 product, you really are speaking about 4 strings, the 3 that come in and the 1 that is the product. This is associated to a moduli space of 4 interacting strings, which is the moduli space of 4 strings in a sphere, is just the complex plane in the position of one of the punctures. So you need two anti-ghost insertions to compensate for this moduli. So for each modulus, which is equal to n minus 2, because if there are three things here, it's like a 4-point function, you have two moduli, and this number of anti-ghost insertions. Two anti-ghost insertions for each complex modulus. So you have that, and will play a role. So let me show you the full identity. The signs are correct here. And so that doesn't mean there are no other conventions, but this B1 plus Bi minus 1. So here it is. The failure of this to derivate is these two terms that I'm going to write here. B1 up to QBI up to Bn. That's the failure of this thing to derivate. And here comes the generalized Jacobi identity. Sum over IL, partitions, IL, JK, sigma, a sign factor, IL, JK, BI1 up to BIL, and then the second bracket, BJ1 up to BJK. This whole thing equal to 0. So this is a Jacobi thing, two brackets. So what do you have to do here? You're supposed to take, you see, all these things are graded commutative. So you can, the order in which you put them doesn't matter up to a sign. So you basically have the n inputs, and you have to break them into two groups. Select 5 of them, and 3 of them if you have 8. And then put those here, sum over all these splittings. And this sign factor is the sign to rearrange this sequence QB1 up to Bn into BI1 up to BIL, Q, BJ1 up to BJK. Please ask me if this is not precise, if I forgot to say something. All the splittings, so the order of the splitting doesn't matter, just the elements on each splitting, because you won't sum for different positions here. So you grab all the string fields, you take a few, you call them I1 up to IL, and there's the sign in which you would move these things in order to put them in this order. It's here. So this is, in fact, the general identity of a homotopy Lie algebra. The generalized, the first, if you take this with 3 string fields, you will get this identity with its proper signs. If you get it with 2 string fields, you will show that Q is a derivation. And, well, it looks a little cumbersome with signs, but with a little bit of BV technology and some good notation, you can convince yourself that the action equal 1/2 psi cube psi plus 1 over n factorial, well, sum from I equal 3, n equals 3, to infinity 1 over n factorial psi up to psi with n minus 1 psi's here is the full action. So 3 and 1, yeah. And the full gauge transformation is delta psi equal q lambda plus sum from n equal 1 to infinity of 1 over n factorial lambda psi n of those. So the action is not tremendously difficult to write. It's here. The gauge transformation is not very difficult, and this identity guarantees this gauge invariance. So
is this even good for small size?
well, certainly for small size, perfectly good. You can do perturbation theory, reproduce the Polyakov theory. Everything is good for.
You know something about how size by size grows?
Well, we don't know too much, but certainly if we use it in the path integral language, we'll reproduce the Feynman expansion. There's been less evidence, however, that this theory has solutions that lie far. Some partial evidence. Yuji Okawa and myself did one of these orbifolds that Joe used to do of type 2, in which a cone flattened up, and we found some evidence that this described it. The evidence was not very clear because it's all sort of approximate. You work with some number of terms and try to hope for the best. But we don't know. Yeah.
Now you have some instant modular things, and there's clear some arbitrariness there. So you got to speculate some arbitrariness in the definition of the total product?
Absolutely. All the products can be redefined and changed, and if you change them, you get different decompositions of moduli space. Now, certainly in matters of proving that something gives you a cell decomposition of moduli space, you have to choose some convention because you're not powerful enough to do it in general. So I'm going to show you, just to finish up this discussion of closed strings, how the vertices look. You know, most explanations of string field theory go through the open string and they come to the closed string and say, well, it's similar, but it's a lot more difficult, so that's it. Let's not discuss it. I want to show you just for you to see the vertices, how they look. And you will see that, at least conceptually, they're extremely simple. And computationally speaking, they're difficult, but in a sense, I gave you a picture here. We can give you a picture for all the higher ones. So, and then we'll leave it there.
But
yes?
What's the relationship between this story and the A-infinity algebra?
The A-infinity algebra is the homotopy associative, which is the version, if you took Witten string field theory and didn't insist on associativity, but you had higher terms, you used the product was not strictly associative. You could fix it by a higher product and then write a very analogous non-polynomial algebra, and the identity that is over there would look a little different, and those would be the defining identities of the A-infinity algebra. Sorry?
Why would you want to do that?
Well, at this moment, we probably don't want to do it to find classical solutions because this action looks more complicated. The advantage of an A-infinity structure is that associativity has always been delicate. Some string fields are not associative, but homotopy associativity is a lot less delicate because you keep things sort of away from the midpoint. You never talk about the midpoint. It's sort of safer. Another side, either complication or advantage, is that the closed strings must be added by hand once you put an homotopy associative open string field theory, because essentially you sort of separate the open strings. You don't let them collapse enough to create closed string poles. You may view that as an advantage or as a disadvantage. It's not clear. Certainly, closed strings, when they appear in Witten string field theory, they appear in a rather singular way, and that has been our fate. Well, if I define the classical open string field theory action with I've been calling little stubs in the vertices, this action will not satisfy the Batalin-Vilkovitsky master equation, and the only way to fix it at the quantum level is adding the closed string. So, physically, that's exactly true. Okay, so pictures. I want to describe this picture because it's pretty. So we have here. So how did we describe three open strings interacting? Well, three open strings interacting, we describe them like this. And what was this picture supposed to be? Strictly speaking, it was a joining instruction. I told you last time you had three strips, three semi-infinite strips, and these are the joining instructions for these edges of the strips. And then you got your three-string vertex. For closed strings, we essentially alluded to the joining instructions, and you would draw them like that, three closed strings like that. You would, if you wanted to be a little more pictorial, you would add three infinite cylinders, but if you want. But really, better to stick to this graph only and think of three semi-infinite cylinders that are like here, and that's, say, one, red, and that might be this one, and blue, the joining instruction. Here, is that right? So that's the joining instruction and defines the vertex completely. Well, what is the 4-point vertex? The 4-point vertex is the following joining instruction. You can guess it. It's a tetrahedron. You must glue one string to the bottom, one to each face. Nevertheless, you're sought to produce a region of the moduli space. What do you know? All these closed strings have the same length, 2 pi. Well, if you have this thing and all of the sides have the same length, you will convince yourself you have 4 constraints and 6 edges. So you have A, length B, C. You will find that this, maybe I should do dotted, otherwise nobody will know which way this is. This is A, C, B. Each face has ACB, ACB, ACB. And A plus B plus C is equal to 2 pi. So this is the joining instruction, and now you see part of the problem. When you had the product of two strings, 2 points were enough. Now strings sort of interact at 3 points. Each string is joining other string at 3 points. So this is going to get more interesting. Now, here it is. Each face has circumference 2 pi, because all closed strings have circumference 2 pi. And the region of moduli space, you would say, okay, here is A, B, and C. The region of A plus B plus C equal to 2 pi is this. 2 pi here, 2 pi here, and 2 pi here. The region of moduli space that you need for this vertex, so this is the joining instruction, but A, B, and C vary subject to this constraint and one more inequality. The inequality is that every non-trivial closed path in this polyhedron must be longer than 2 pi. So for example, you have a closed path that goes like this and closes here. It must be longer than 2 pi. So this is C plus B, 2C plus B, must be greater than 2 pi, which means C plus B must be greater than pi, which means A must be less than pi, B must be less than pi, and C must be less than pi. Well, that's a little triangle here. This is the region that you must integrate. So let me summarize. What is the interaction? This graph, cylinders coming in, integrate over this polyhedron that has faces all of perimeter 2 pi, and where every closed path that you can imagine, non-trivial closed path, is longer than 2 pi. So it's a polyhedron that each face has 2 pi, and you cannot find a way to go around non-trivially to be shorter than 2 pi. Yes? The two edges of what?
Of the same length.
Yes.
Follow from the sound to the circumference of the triangle.
Right. That's right. If you put 6 variables and you put 4 equations, you will find this solution that I wrote. So that's a 4-point function, and the 5 is not more complicated. It's a polyhedron with 5 faces, all of whose closed non-trivial paths are greater than 2 pi. That's the same for 6, for 7, for 8, over. That's it. That's a description of all the interactions. So you have a very clear picture of what each interaction is at each level. Whether you could compute them, it's a lot harder, but the picture is clear. So I'm done with closed strings. I'm going to move on. This implies that A must be less than pi, B must be less than pi, C must be less than pi, and that's that triangle over here, is the barycentric subdivision. If you want a little more details, I could tell you the following. This is part of the moduli space of 4 puncture spheres, because you have 4 cylinders. So this is the region provided by this vertex. This is the S channel, T channel, and U channel, and this is the whole moduli space. It's a theorem of Strabel that if you form all the polyhedra with all possible size lengths, subject to this constraint, you cover moduli space. So that's it. If Strabel says, in this picture, you get the whole thing. But you only need this part because these parts are produced by ST and U. And it's sort of very pretty how it all works, even though it's very detailed. So that defines the classical theory. We could talk about the quantum theory, but I don't think we should do that. I move to superstring now for a little bit. Yes, Gary.
If there is a picture that if you go to the tactile vacuum, there's a theory that we know open string states, but they have closed string states.
Yes.
So I gather that is there any evidence that this type of structure emerges from the open string?
Not really very clear evidence. You see, closed strings appear very through the back door in open string field theory. So people have done some analysis and tried to take the open string and move it to the vacuum and try to argue that the perturbation theory sees no open string states, but perhaps some complicated closed string states in open string language, but nothing yet. Nothing pleasant has happened yet about that. Okay. Move to superstrings. So what happens with superstrings? Well, there's some interesting complications as well. So Neves-Schwarz open superstring. So basically, I'm describing work of Nathan here, and let me begin by the standard lore about superstrings. There is the complications in superstring theory of a beta-gamma system of superghosts. And these are first-order system. The conformal field theory has just one derivative, but they're bosonic, and that causes all kinds of difficulties that are led to, these are bosonic, to a fermionization, in which you introduced beta was written in terms of a psi field, a phi field, and gamma, eta, and phi as well. So you trade beta gamma for psi, eta, and phi. And, well, that's part of the story. There's these things, these phi's carry picture number. A very natural definition of picture number for these things is that this has picture number -1. These have 0 picture number, so this has picture number +1, eta -1. We'll do a little table to make sure we get all these things right. But if you were doing the conventional BRST approach to open superstrings, you would say, all right, by now open string theory Q on the state killing it seems the right field equation. And indeed, people look at that and they say, well, phi in the Navier-Schwarz sector is typically a ghost e to the -phi and a matter vertex operator on the vacuum. That's the canonical Navier-Schwarz -1 picture because of the minus e to the -phi. And this thing is dimension 0. This has dimension -1. E to the -phi has dimension 1/2. And the matter vertex operator has dimension 1/2. A typical state could be a C1 e to the -phi, a psi mu -1/2 oscillator or something like that. So this is this thing, if this is a matter primary of dimension 1, well, it will be BRST invariant, and this is the canonical field that we imagine. So the thing to remember about this field is that it has ghost number of this field is equal to 1. We won't have ghost number with this, and picture number, and I'll call it P, equal to -1. And probably I should do the little table now. If you have psi and eta, and you have the dimension, the ghost number, and the picture number, this is a dimension 0 field, a dimension 1 field, a ghost number -1 field, you can see it from here, ghost number +1 field, picture number +1, picture number -1. This has picture, so this has picture -1. If I put here e to the -q phi, well, the dimension has a little complicated formula. The ghost number is 0 and the picture number is -2. Okay. No. C and eta are these anti-commuting fields, and dimension 0 and 1. This is dimension -3/2, dimension this is -1/2, this is +3/2, 0 picture, ghost number -1, ghost number 1. I see. Okay. All right. Now, correlators need picture number, total picture number -2. The non-vanishing correlator on the disk is something like that. See? So you need ghost number 3 and picture number -2. So you seem to be in fine shape here, and you could try to do an action in which you have 1/2 phi hat. Now this is the open string inner product. No C0 minus here, nothing like that. Q phi hat. That looks good. Picture minus 1. Picture minus 1, you got your minus 2 picture. Goes number 1, goes number 1, goes number 1, you're fine. But as soon as you try to write the interaction, some sort of phi, 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 well, you've got 3 minus 1 pictures, and you need to add a picture changing operator, usually called x, that has picture equal plus 1. And that's where all the problems begin. Yes? No, this is the small Hilbert space yet. This is, we'll put the psi a little later. You see, at this moment, only the derivative of psi appears here. So we're using just this thing. So you need a picture changing operator. You have to insert it. The only place you can insert it is in the midpoint. Creates a big trouble with the gauge invariance, and people have tried to work. I think Arefeva, Medvedev, and others work in picture minus 2 or picture 0. They tried different pictures to get picture changing operators that collide better. And anyway, it's a difficult thing. So here is the idea to try to fix this problem. We'll try to use a string field that has picture 0. And that looks a little difficult, but it would be very convenient. So in fact, you want a string field that is so simple. We want a string field now that has ghost number 0. We want a string field and picture number of the string field 0 as well. So how are we going to do that? Well, we're going to try to work on what is called the large Hilbert space. So remember psi has picture number plus 1. The natural string field over here has picture number minus 1. So if somehow you have in the back of your mind the idea that phi that you want could be something like psi times this field, you would be in good shape. You see the ghost number and the picture number would be fixed, because this has ghost number minus 1, this has ghost number 1. You go to ghost number 0, and picture number, this has picture minus 1, picture plus 1, and you would be in good shape. So since we're talking about a large Hilbert space, the large Hilbert space includes psi 0, which is the 0 mode of the psi field, another anti-commuting 0 mode. Now, if we're going to include this anti-commuting 0 mode, we are going to have a larger space. Certainly the space is at least going to double, because you have one more 0 mode that you can add to any state. So you need more gauge invariance. So the idea is to have two gauge invariances, one generated by Q, that squares to 0, and one generated by the 0 mode of this dimension 1 primary. This 0 mode of this dimension 1 primary is anti-commuting and also satisfies, therefore, it only has non-trivial OPs with psi, so eta 0 squared is equal to 0. You should also, of course, note that psi 0, eta 0, anti-commutator is 1. So here is the real change that is happening. The real change that is happening is that while for open bosonic strings we had one derivation, Q, we're going to have 2 and 2 gauge invariances. So we're going to go to a larger Hilbert space to allow ourselves fields that don't have those number and those have picture, and we're going to need more gauge invariants. So let me justify this a little more by showing you the linearized field equations. Now, the linearized field equations will be of the form, one more thing. Q and eta 0 anti-commute. You need the expression of Q to see that, but it's a fact. So what is the equation of motion? Q eta naught phi equals 0. That's the tentative equation of motion. Let's try to see if it makes sense. Well, this equation of motion has 2 gauge invariances. Phi goes to phi plus q lambda, and phi goes to phi plus eta 0 omega. Those 2 linearized gauge invariants. Now, if you have an invariance of this type, you can choose a string field that is annihilated by the other one. You can make psi 0 annihilate phi. And that's clear because if it didn't annihilate phi, you add to it minus eta 0 psi 0 phi, which is something of this form. And now look, you add with psi 0, you get psi 0 on this. You add with another psi 0, you get the 1, and you cancel it. So you certainly can make this of this form. So you can make this annihilate this state. Now, since psi 0 has no cohomology, you can now write phi as psi 0 times another one. Has no cohomology. Now, this thing is invariant, this result is invariant if you add to it anything with psi 0. So here there is a gauge invariance as well. This can go to this plus psi 0 times anything. So with this gauge invariance, you can choose this so that it is annihilated by eta 0 this time. You see, when you have this invariance, you can make it annihilated by this. When you have psi 0 invariance, you can make it annihilated by eta 0. So eta 0, and you can choose phi hat so that eta 0 kills it. So I don't want to erase some of this. So what do we have in summary? We have learned from this analysis that phi is equal to psi 0 can be put in the form psi 0 hat, where eta 0 of phi hat is 0. And now you see that we basically realized this thing that we wanted there. If this has picture 0 and those numbers 0, this thing will have, because of this, picture minus 1 and those number 1, which is the conventional state. Let's go back to the equation of motion. Q eta 0 phi now becomes Q eta 0 psi 0 phi hat. The anti-commutator gives you 1, and this annihilates phi hat, so you get Q phi hat equals 0, and you've recovered what has been claimed to be the conventional set of states. So we've gone to a larger Hilbert space, we've proposed a linearized field equation, and it gives you what you want. So the only problem now is constructing the nonlinear theory, preserving these two gauge invariances, or extending those two gauge invariances. I will not build it really, but discuss a little bit how it's formed. So first, the equation of motion. The equations of motion are very simple. So this theory is called Wess-Sumino-Witten-like models, two-dimensional Wess-Sumino-Witten-like models, in analogy to that two-dimensional field theory that has holomorphic and anti-holomorphic derivatives. Here would be Q and eta 0. So while open string field theory used to be Chern-Simons, closed string field theories, Lee algebras in homotopies, this is two differentials. And that's the sort of structure of this theory. And Warren looks like smiling there. No, I haven't. So, what is the equation of motion? The equation of motion is quite pretty. It's eta 0, e to the minus phi, q, e to the phi, equals 0. Now, it requires a little bit of notation to see what you mean by this. But look, if you have a string field that has those numbers 0, and picture number 0, this thing is some object of those number 0 and picture number 0. And the exponential is defined through the star product of Witten, the associative star product of Witten. So a little ambiguity maybe that you might think, so what is the leading term? It would be 1. What is 1 here? You can think of it as the identity string field. But you don't have to bother because Q annihilates the identity, so this really begins with Q acting on phi. And this is 1 times something, so this is something that is basically Q phi plus things more complicated than that. So this is the field equation. Now, a little about the action. The action, we have to remember one thing that Martin already alerted us. If you had in the small Hilbert space C, D squared C being different from 0, now you have the 0 mode of the psi, so you must insert one more psi in here, and that's different from 0 in the large Hilbert space. So this has ghost number minus 1. So you need something of ghost number plus 2 and picture minus 1 in this framework in order to get non-zero correlators. Ghost number, you have 3 here, minus 1 is 2. Picture, you have minus 2, but plus 1, picture minus 1. So how does the kinetic term look? We wrote just the action like that, but the kinetic term, S2, is roughly like eta phi q phi. And that works well. Yeah, of course. This has ghost number 0, ghost number 0, ghost number 1, and eta, you see there, ghost number 1, so you got ghost number 2 right. Picture 0, picture 0, picture 0, picture minus 1. So you got this right. This would give that linearized equation of motion. The full thing is Wess-Sumino-Witten, so we can write it. It takes a little notation. Let me put this notation here. Small details on the notation. I might as well show you the looks of the gauge transformations. The gauge transformations that we had here, two parameters, break into two pieces. These things don't really mix. Delta of e to the phi is easy to write, not delta of phi. And that's q lambda times e to the phi plus e to the phi times eta 0 omega. That's the nonlinear version. Finally, we can write the action. And I want to make one comment here that is rather interesting, is that this field equation has a rather nice structure. If you think of open bosonic strings, this is a ghost number 0 string field. Remember open bosonic strings. What did we have? We had this equals q lambda plus lambda star phi minus phi star lambda. This was ghost number 1, and this was ghost number 0. This is for the gauge invariant. Now, if you formed here e to the minus lambda q e to the lambda, which is a natural thing to do, because this has ghost number 0 in open bosonic strings, this would be called a pure gauge solution of open bosonic string field theory, because this would be ghost number 1 built with a gauge parameter like that. So this, in a sense, is formally a pure gauge string field in open bosonic string theory, built with the ghost number 0 field now, because in the superstring that's ghost number 0. So that's structurally the answer. Now the action, of course, takes a little more. You have to define two small ingredients. So let's see that. Just in order to write it, I think it might as well see. If you define AX to be e to the minus t phi, x e to the t phi, t is a number that will go from 0 to 1, and x is an operator that is a derivation. So if you put q here, it would be e to the minus t phi, q acting on this exponential. And this is analogous to the things in Wess-Zumino-Witten in which you have g minus 1 dg, basically. And you use a derivation, and you have x. And your derivations, of course, x could be q, could be eta, and in fact could be p, if you think what that may mean. At will define as e to the minus t phi, dt formally of e to the t phi. Now, of course, that's a simple thing, but it's okay to write it like that as well. It's just phi. So here is the action. Integral from 0 to 1 dt, dt a eta aq plus at aq anticommutator a eta. Now, it may seem, what you recall is that you need this sort of, in Wess-Zumino-Witten, this sort of T homotopy just for the interaction. Indeed, that's true. Here's a total derivative. So I could have written this evaluated at T equal 1. But here is the sort of Wess-Zumino-Witten term. And if you play with it a little bit, develop a set of properties, it's not too difficult to show the motion follows, the gauge invariant follows, but it takes a little work. the structure is it's a little sophisticated. So that's open superstrings.
What are the double brackets?
The double, this is a strange notation, because here it just means you're going to supposed to take the correlator and every product is evaluated with a star product. So this is gauge invariant. Now, the bosonic strings, the quantization can be done with Batalin-Vilkovitsky quantization, and the result is really quite beautiful in the following sense. You start with an action, and you have a string field of gauge number 1, and the gauge fixed quantum action, you just need to relax the condition on the gauge number of the string, and the action is the same. But now the string contains all gauge numbers. That is not obviously true in this action, and the quantization of this action, the Faddeev-Popov of those goes for goes, the structure, whether you should relax the picture, that sounds hard. I don't know. The question is how to do this Faddeev-Popov quantization of this. So you can sort of do and understand things well there, but in loops I think it's still not clear how this action will work. But being gauge invariant, reproducing the spectrum, and all these things suggests that probably if it's understood, it will work out. Yes, guys?
So in Witten's bosonic open theory, the moduli space is covered by the simple field.
That's right.
The bosonic called superstring is the same. And yet there's many more actions.
Yes.
The moduli space is still covered.
Yes, all these interactions introduce no moduli. Like the closed string interactions filled missing regions. Here they don't. So this 4-point interaction, 5 to the 4th, with all these things, is on a fixed Riemann surface. It's 4 strings coming together, no integration over moduli. The effect of this interaction is somehow do something with the supermoduli in a very clever way that I don't understand. Somehow it's moving. In a normal picture, you would have to move picture changing operators from one side to the other of the diagram. These terms are helping you do that. And I think Nathan has computed amplitudes and maybe can say something about this. Because psi is near phi now. All right, so 15 minutes for heterotic strings. Okay, so what changes now? All these ghost numbers and conventions may be dancing in your head, but I hope not too much. So let me leave this here. Table is always useful. So heterotic there's one thing that is probably interesting to note here is that eta and q enter in the same footing in this theory. They're really completely symmetric. Eta and q are both derivations of the star product, both square to 0, they anti-commute. It's very simple. Now, how are we going to do heterotic string field theory in Evers-Schwarz? Well, we'll try to tensor a phi of the open superstring with a phi of an open bosonic on the right sector. So let's remember what we had here. This phi was Grassman even. This one was Grassman odd. This one had ghost number 0. This one had ghost number 1 This one has picture number 0, and this one has picture, no picture even, doesn't apply on that side, of course. And now we're going to form, therefore, naturally, a string field, heterotic string field V, that should have, given this tensoring nature, we expect it to be Grassman odd, ghost number 1, and picture number 0. If you want to see how this, moreover, this is a closed string field. So we cannot do away, unfortunately, from B equals L0 minus L0 bar, B equals 0 either. And whenever I will write something like AB, it must have the C0 minus. Now this is certainly right for describing what we want. You can see it as follows. At least the natural vertex operator V, we know its picture number is Neves-Schwarz sector. This has picture 0. We know the V has a psi, that's the usual vertex operator. The usual vertex operator will be CC bar, e to the minus phi, matter on the vacuum. And this is the usual heterotic string stuff, and that's supplemented by psi as before to get picture number 0. So we certainly want still an equation of motion of the type eta 0 q, or q eta 0, v equals 0 at linearized equation of motion. Why? Because we still want to physically be able to get rid of psi and get to the conventional string field, which satisfies standard q equals 0, and the steps are really identical to the steps I did before. Now, how about this thing? This changes a little bit. It now has just psi e to the this, and we have c bar, d c bar, d squared c bar. So correlators must have ghost number 5, actually 6 minus 1, and picture number minus 1. So what can we write? Well, S2, it's simple actually, it's eta V QV. Let's see why this works. Well, you would expect eta to be self-adjoint in this linear program, so you would get this field equation. Let's look at the quantum numbers. Ghost number. This has ghost number 1, 2, 3, eta 4, and the C0 minus 5. So you'll find here. Picture number minus 1. That basically tells you that each term you're going to write at most can have 1 eta because it produces negative pictures. And we'll go on with that. So this is fine. This is S2. How about S3? What can you write? Well, you don't run into too much trouble with S3, and you can write eta V, and now you have the closed string products. So you want something with V and V here, a cubic thing. Now remember, this is graded commutative. This is closed string field, and this is Grassman odd, so that would be 0, so this is not good. You must have some Q in there. In fact, 1 Q will do. And let's see what you get now. Look at the ghost numbers. 1 plus 1, 2, 3. The star product reduces one ghost number, so this is back to 2. Now, you don't have to do more arithmetic. This was ghost number 2, and this is ghost number 2, so the numbers work. 5 minutes is probably enough to finish this. So the next term, I think, still is worth writing it a little bit. And here is when things become sort of interesting. S4, 1/4, and here comes eta V, and you have V, 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 is the triple product of closed string field theory. Now, how can you fix this? Of course, this would be completely equal to 0. You cannot even tolerate having one Q would not be enough because this is graded commutative. So you better have 2 Qs. So the Qs are starting to proliferate. Now, will that work? Remember, the triple product subtracts ghost number -3. 1 for the B0 minus and 2 for moduli. So you have 2 ghost number 2, and 1 is 5, -3 is ghost number 2, which is again good. You need the second thing to have ghost number 2. So you're fine. But this would be very close string field theory like, just the quartic interaction. But that doesn't produce gauge invariance. You need to add one more term, plus eta V, and this one, the sort of the Jacobi term, must be there as well for the gauge invariance. You see that the symmetry between eta and Q has been totally destroyed. And the reason is clear. Eta is still a derivation of all the products of the closed string field theory because there's no supermoduli. But Q fails to be a derivation, so Q has to work differently. So the ghost number here works well as well. This is 2 and 1, 3. Minus 1 is 2. Plus 1 is 3. Minus 1 is 2, and you're fine. So this... no bracket missing. This is the triple product. 3 close... No, but the triple product is one string field. 3 inputs, one string field. Is that right? Anything in here must be one string field and one string field. This is the triple product of 3 string fields giving you one string field. No, it's just saying that 3 string fields can be made to interact this way or this way as well. And this term is also needed for the gauge invariance. Well, remember when we had the triple interaction, it was related to the failure of the Jacobi of 2 brackets. So both are present here. This is in bosonic string theory, this would not have enough moduli. This has moduli, but this has no moduli because it's just a 3-point interaction iterated. So it's very surprising.
What about the level maximum?
Oh, it appears in the moment you've defined the product, you've always imposed a projector to L0 minus L0 bar and B0 minus B0 bar implicit. B of course satisfies. Yes, sure. Yes, it definitely. Yes, yes. In the inner product. Whenever I write an open string inner product has no C0 minus. A closed string inner product has a C0 minus. That's why we got the 5. You see, we had to get ghost number 5 according to that rule, and we have 1, 1, 1, 1. It's missing 1, but the C0 minus is there. Okay, let me try to wrap up. Well, with UG, we did this work, and we got the 5-point interaction, and got more complicated, and it seemed that it would be very difficult to guess what is the complete answer. But then Nathan came to our help, and we wrote a paper, and it was all completed. It's a little exotic, but at least the field equation, remember the field equation for the open thing was e to the minus 5q e to the minus 5. Which one? This one was black. For the heterotic string, the field equation is eta 0 times something that we call psi q bar, which is a pure gauge closed string field. You see, remember here, this is ghost number 0, and it's the right thing to be thought as a gauge parameter of open string theory. In closed string theory, a gauge parameter is ghost number 1. So you take the string field V, think of it as a gauge parameter, make a pure gauge closed string field, eta on this equals 0. This will produce this whole series in the right way, and will give you the answer. No, it's not separate the gauge invariant. It's in order to fix the gauge at order 4. Yeah, no, nothing stops. You see, at least in the closed string sector, you need all the vertices to fill the moduli space. So it would be very suspicious if you would be able to stop before. Would be very strange. So let me conclude by saying a couple of things about type 2. And it will be 3 minutes. It's something that doesn't work, but maybe with some cleverness it will. But let me tell you what more or less happens there. So you would think naively that for type 2, you could tensor as open super to an open super. That is at least naively the case. And then the string field, we could call F, would have picture change in total picture 0, total ghost number 0. And this time, the total thing that must give you non-vanishing inner products is this. C phi bar C, d C, d squared C, C bar, d C bar, d squared C bar. That's different from 0. And that has ghost number 4 and picture equal minus 2. Well, this calls for something really pretty and different, but we don't know what it is. So at first sight, the obvious thing that you're going to do is try to get a field equation of the form Q, eta bar F equals 0, because you have to remove from the string field 1 and 1 and that. So now you have 3 things. Not 2, like for open superstring. You have something geometrical with 3 things. Okay, well, this actually seems to go through at the beginning. This is Grassman even. And look, at the beginning you have F. You could put F, Q, eta bar F. Let's see the ghost numbers. Well, this has ghost number 0, but we have 1, 2, 3. C0 minus is 4. You're fine with ghost number 4. Picture minus 2, the eta and the eta bar. You seem to be okay for a quadratic term. Well, but then things... Now, this is very strange, because I've always believed that if you can get the quadratic things to really work, you don't find trouble later. But you do find strange trouble later if you go this way. let me explain what it is. Now, suppose you want to go to an interaction. Suppose you want to go next step. Let's see, eta bar f, and you want to put 2 more f's to get things to work. Well, actually, you need 2 q's. Let's see that. Let's see if we can see it at least. You can think of this, let me put it some other way. Eta bar f, qf. The same thing, I've moved around things. So this must have ghost number 1. Well, this has ghost number 0. This has ghost number 0. And this reduces the ghost number by 1. So you'd land, if you would have it like that, this is okay, but you would land with ghost number -1, and you want ghost number +1. So you can put 2 q's here. You think you can put 2 q's here, but actually you can't, because this is Grassman even, and this is odd, and this would vanish. But it's not a terrible failure. You can put the q on this side and survive. But then if you go one more, eta f, and you go f, the ghost number now of this intrinsic thing is -3. So this thing now needs 4 q's to lift it to ghost number. 1 q can go here, you need 3 q's here, but now this vanishes. So you cannot write the terms you want. Something has gone wrong. Seems we're doing the wrong thing. We never wrote, of course, our attempts. They fail very obviously. Probably the reason is that in a sense, in closed string theory, if you even think of closed strings, bosonic closed string field theory, it's not really the tensor product of 2 opens, but it's sort of the tensor product of a gauge invariant open with a gauge fixed open. Because you get the C0 that is telling you something with gauge fixing. So maybe a better strategy to be to finally, somebody should do the job of quantizing Nathan's thing, and then try to tensor the gauge invariant WZW with a gauge fixed WZW, or something more imaginative must be done here. So that concludes the lecture. Thank you very much. Right. Correct. Just never short sector even. We cannot get it to work yet. And it would seem nice if it could. Yes, Michael. That's the cubic what? Oh, the Witten. So, nobody I think has tried it since the cubic open superstring its bill of health is not too good. I don't know if people want to do that, but maybe it will work. Anything, maybe heterosis should be a little more imaginative, and we should do it better. But it doesn't look like a terribly complicated problem. But once you get to the details, you see that heterotic string theory was very natural, and this one something. You need too many q's. You see, basically, you're trying to a field of picture -2, because you see what the q's do. You have the psi and the real things, or the psi bar. The q is psi, this is the picture changing operator. So actually, you need too many picture changing operators, and they cannot be sort of carried by q because it squares to 0, and you cannot put too many q's in here. This proliferates. If you go to higher and higher interactions, you have n string fields, and you need order 2n q's in order to get the right ghost number and to clean things. So somehow, people have suggested to me what happens in closed string field theory if you try to do q left times q right psi equals the kinetic term, all kinds. This would be suggested by WZW. You use eta 0. Both are nilpotent, but this has never worked. And there are all kinds of elegant proposals that never get off the ground. And I don't think we probably have to invent something terribly sophisticated to get the type 2, but who knows? Gary?
The nonlinear field equation can be written in terms of the Fourier form. It's very suggestive. It's like a large leap sensitive.
Right.
You do set out 3 dimensions and solve
Other Chris? No. You see, the Witten form cubic theory, he could do the Ramon sector with a lot of more picture-changing operators. When Nathan tries to do the Ramon sector, he has to sort of break a bit the Lorentz invariant. So I guess in this formulation, you don't have something fully Lorentz invariant if you have Ramon. So since we don't want to go the route of picture-changing operators a la Witten at this moment, we just try to solve even the simpler problem. Now, it has... why? I don't know exactly why. Nathan can say, but there's one thing that you should expect, that while I think that it doesn't require an incredible imagination to solve this problem, the Ramon covariant string field theory is going to solve the problem of writing a covariant formulation for the five form, self-equal 5 form, which essentially nobody knows how to do. So if that string field theory could be written in the Ramon sector covariantly, that's going to be really surprising and quite amazing. So if you break some Lorentz symmetry, maybe the 5 form is more tractable. That may be the reason. Nathan, you want? All right. So, stop here.